Hello everyone, welcome to Elevate Techie Data Science series. In previous video, we have seen what are hyperparameters and what makes them different from the model parameters. In today's video, we'll explore various techniques for hyperparameter tuning and demonstrate how to implement them using the Python code. As we seen previously, hyperparameters are the parameters that are set before the training process begins, and tuning them can significantly impact the performance of our model. So there are various techniques available for hyperparameter tuning. So let's see what are those. So first one is the grid search, and next is the random search, and later we have the Bayesian optimization and the gradient based optimization. Now let's look into the grid search in detail. By definition, grid search is a systematic method for tuning the hyperparameters by searching through a manually specified subset of hyperparameter space. So how does this grid search work? Firstly, in grid search, we'll be defining a grid of hyperparameter values that we want to explore. Once the hyperparameter values are defined, then it will perform an exhaustive search for the overall possible combinations of these hyperparameters values that we have set. And next, for each combination, it trains the model that we have built and it evaluates its performance using this cross-validation technique, and it finally selects those combination of hyperparameter values that yields the best performance for the model. So this is how grid search is performed. Now let's see practically how we can implement the grid search. So for this, first we'll be importing the grid search from the sklearn libraries, and then we'll be loading the data set. Here I am loading the iris data set and I am defining the features and the target values. So here X are my features and Y is my target value. And after that, I will define the hyperparameter grid. So for the grid search, as we previously mentioned, first we'll be defining the hyperparameter values. So here we are defining the hyperparameter values using the param grid. And next what we have to do, we have to build a model. So I have built a random forest classifier model here. And after that, what grid search basically does is it performs the search for all the parameter combinations for which we have defined in the hyperparameter values. So here I am doing the grid search for all these hyperparameter values, and after that I will be fitting that to the model which I have built, and finally it gives us the hyperparameter value which gives the best performance score for the model. So it is giving me here the best hyperparameter value which gives me the best score for the performance of the model. So this is how we can implement practically the grid search in our model. And next we have the random search. So previously in grid search, we are performing the search for all the hyperparameter values we have defined. But in the random search, it simplifies the process of hyperparameter tuning by randomly sampling the combinations of hyperparameters from the predefined space. So let's see how it actually works. Random search basically differs from the grid search in a way that it doesn't explore all the possible combinations, but it randomly chooses the specified number of the combinations from the hyperparameter space and then it evaluates their performance. Random search is basically more efficient than the grid search when the hyperparameter space is large or when the same parameters are more influential than the others. Now let's see how the random search is implemented in a code. So for the random search, first we need to import it from the sklearn libraries, and after the random search is imported, then we will be loading the iris dataset and we'll be defining the hyperparameters in the same way as the grid search, and then we'll be building our model. Here we are using the random forest classifier and we are performing the random search over here. So instead of the grid search, we are using the random search and we'll be defining the hyperparameter values which we have defined previously, and we'll say how many iterations it has to perform, and later once this random search is done, we'll be fitting that to our model and it will display us the best hyperparameters which fits for our model. So this is how random search can be implemented for our model. Later we have the Bayesian optimization. So Bayesian optimization basically is an iterative model based optimization technique, which will leverage the probability methods to search for the optimal set of the hyperparameters. So let's see how this basically works. It basically works by building a probabilistic model of objective function, which is a performance metric, and using this model to guide the search for promising regions of the hyperparameter space. So by sequentially evaluating the objective function at selected points, Bayesian optimization learns from the past evaluations and focuses the search on the areas likely to contain the global optimization. So now let's see the practical demonstration of this Bayesian optimization. So first we have to import this Bayesian search from the skopt libraries, and after that the same way we are loading the iris dataset, and we'll be defining the hyperparameter space here, and we have built the random forest classifier model, and we are doing the Bayesian optimization search here. So for the Bayesian optimization search, we'll be giving out our model and the hyperparameter space which we have defined, and then we'll be performing the fit for this model, and then it will display us best hyperparameters which gives the best score for the model. And the last technique we have is the gradient based optimization. So gradient based optimization offers the most sophisticated approach by treating the hyperparameter tuning process as the optimization problem. So let's see how this works. So gradient based optimization basically treats the hyperparameter tuning process as the optimization problem. And in this, the objective is to minimize or maximize a certain performance metrics. So it leverages the gradients of the performance metric with respect to the hyperparameters to iteratively update the hyperparameters in the direction that improves the performance of the model. So by iteratively updating these hyperparameters based on their gradients, gradient based optimization method aims to find the optimal set of the hyperparameters that maximize or minimize the performance metrics. Now let's see the practical demonstration of this gradient based optimization. So in this we'll be importing the necessary libraries here, and then we'll be loading the data set, and we'll split the data set into train and the test data. So in this we are basically using the random forest classifier as our model, and we define the objective function which will take the set of hyperparameters as the input. So here we are defining the objective function where it is taking the set of hyperparameters as the input, and we train the model with these hyperparameters, and it returns as the negative accuracy which is to be minimized, and we then use this minimize function from the skpy-optimize to minimize the objective function which effectively performs the gradient based optimization. So here we are performing the gradient based optimization using this minimize function from the skpy-optimize. So after that we are storing the result, and finally we extract the best hyperparameters and the corresponding accuracy from the optimization result and then print them out. So this is how we can implement the gradient based optimization. And in conclusion, gradient based optimization offers a powerful approach to hyperparameter tuning in ML while treating the tuning process as an optimization problem. So these are all the different hyperparameter techniques which are available for us, and we have seen how to implement them. So that's all for this today's video, guys. If you find this explanation helpful, don't forget to give it a thumbs up and subscribe to my channel for more content on machine learning and data science. Thank you for watching the video, and I'll see you in next video, guys.